to thank the organizers for inviting me to talk here. And today I'll talk about observing the localization in the disorder quantum spin chain based on quantum dynamics. And it's half about quantum annealing, but half gating model. Here's the outline of my talk. And first, I will explain our research aim, the purpose of the work, and I introduce some experiments that inspires this work, and then I'll explain models and methods of this work, and after that, I'll show the main results and time evolution based on exact diagonalization, and then the time evolution
quantum circuits. And finally, I'll give some discussion and conclusions. First, introduction. Many body localization, MBL for short, is an extended concept of Anderson localization, which occurs in a single particle system with no interaction. So the Hamiltonian for the Anderson localization consists of the hopping term and disorder term. If there's only hopping term, then the quantum particle in a system, in a lattice, shows dispersive behavior. But when the disorder is very strong, then the wave function localizes. That's the Anderson localization.
It is like the localization in a many-body quantum system with large disorder. But it is still controversial whether there is a true MBL phase, many-body localization phase. But before the mid-2010s, the many-body localization transition was considered
as a continuous transition
because numerical and experimental results support the so-called MBL transition. But after the late 2010s, it was found that the transition point observed before was not a true phase transition point. The system appears to be localized for a long time in the pre-thermal regime. It is like this. When the disorder is small, then it is in the thermal regime. But when the disorder becomes strong, then it goes to the MBL regime, but it's actually the pre-thermal regime. If there is a MBL phase, true MBL phase, the transition point should be much larger disorder in case. So, and it is impossible to decide the MBL transition point numerically or experimentally at the time. Because the numerical simulations or the numerical simulations at the moment, the system size accessible to numerical methods is too small to decide the transition point. And in experiment, it will take too long time to observe the localization. So here we focus on the localization in the pre-thermal MBL regime here. So we focus on the region between here and here. Now let me explain our motivation. Numerical studies of the MBO often suffer from finite size effects. If we could use a large-scale quantum computer, maybe it could be possible to investigate through MBO transition. But current quantum devices are too noisy to compute exact eigenstates to decide the MBO transition. But nonetheless, quantum dynamics can be used to detect many-body localization. You need the memory effect, which is robust against noise, characterizes localization. And actually, there are many experimental works on the many-body localization using quantum devices. For example, quantum mirror, trapped ion quantum circuits, and superconducting qubits, and its so. Now, there are some diagnostics of many-body localization. One is based on highly excited eigenstates. And the first example is this, level statistics. The level statistics shows Wigner distribution GOE in the thermal regime and Poisson distribution in the localized regime. And this right figure shows the level spacing ratio depending on the disorder strings. So this means disorder strings. And the upper dashed line corresponds to the Wigner distribution, and lower dashed line corresponds to the Poisson distribution. So this figure means the level of statistics is corresponds to GOE, the distribution in the small disorder region. These figures show actually the imbalance of probability density. The time evolution of the probability density, which is the experiments of the quantum superconducting quantum qubits. This shows that initially the probability density is 0, 1, 0, 1, 0, 1, 0, 1. So white. And the left figure shows corresponds to the thermal regime because the initial pattern disappears and becomes uniform after a short time. But in contrast, the right figure shows corresponds to the localized regime. The initial pattern maintains for quite a long time, so it looks like stripes. Now, let me introduce another example, which is experiments using DNA. And actually, this work it was inspired by these experiments. And in these experiments, the reverse annealing protocol with a mid-annealing force was used. And the initial state was all spin up or spin down. And after the quench and force quench protocol, the measurement was performed, and we can get the magnetization defined by this. The left figure shows the average magnetization depending on the disorder strength. So the horizontal line corresponds to the disorder strength, weak disorder and large disorder. So this figure means that the system is thermal in a weak disorder regime and localized in the strong disorder regime. Because in the thermal regime, the magnetization is almost zero, because it's in thermal regime, thermal phase. But in the localized regime, the magnetization is nearly equal to the system size. System size is the initial value. So it means it causes by the memory effect. Now, let me explain a little bit about reverse annealing. This Hamiltonian corresponds to quantum annealing Hamiltonian. Here, HTF is the transverse field term, and HI is the incident term for program Hamiltonian. And A here decreases with S, and B increases with S, the parameter S. In the normal quantum annealing or forward quantum annealing, it starts at S equals 0 and ends at S equals 1. So in this figure, this figure shows the reverse annealing protocol, but forward annealing case, it starts from here and ends at here. But reverse annealing starts at S equals 1 and points to some value SE and keep this value, and then finally goes up to the S equals 1. So it's the protocol in the experiments. But in this talk, I'll show only numerical results. So in the numerical simulations, it starts up just here, and not we omit the quench protocol, just only S equals SB all the time in the numerical simulations. Now, let's move on to the model and methods. And the model Hamiltonian is shown as here. L is the system size, and the Hj is the local fields, and it given by uniform random numbers between minus W to W. So W corresponds to the disorder strength. And here in interaction J and transverse field gamma are fixed in the numerical simulations. And here we only use the observables, two observables. One is the magnetization in the Z direction. The definition is here. And the twist over, another one is twist overlap, which is defined by this one. And U twist is a twist operator, and it's defined by this equation. See the shape changes like this. And the point is that these two are easily obtained through the measurement of each qubit in quantum devices, because contains only a sigma to the policy operators. Now let me explain a little bit about the twist overlap. This is the definition of the twist overlap, and it is nearly equal to 0 in the thermal phase or thermal regime, because the new twist side it causes spin wave-like excitation. So, this one is orthogonal to the original wave function, almost. And this one is the schematic picture of spin wave. So it is a long wavelength excitation. And such a long wavelength perturbation gives little effects on eigenstates in the localized space. So in the localized space, the Z is not equal to 0, but has some finite value. So we can distinguish the thermal and localized regimes. Actually, it was found that the twist overlap with sliding eigenstates can detect the many-body localization transition. So we adopt this quantity. Now let's move on to the main results. The time aberration based on what are exact diagonalization. This is numerical work. The time aberration shows the solution of the Schrödinger equation, and the solution of the Schrödinger equation is written as this. And here, psi naught is written like this, and it's the initial state. And here, phi k is the kth eigenstate of the Hamiltonian, and here ek is the eigenenergy corresponding to the phi k. In the numerical simulations below, the initial state is set as the all spin-up state, and the magnetization and twist overlap are evaluated using the wave function at the final time, and the final time was set to here, 10. Now, this shows this slide shows the quantities evaluated using eigenstate for reference. So before moving to the time aberration, just see the quantities using eigenstates. The left figure shows the entanglement entropy, the average, and the standard deviation. And it's plotted as the function of the disorder strength. And eigenstates these are evaluated using eigenstates in the middle energy spectrum. So it's highly excited states. And in the small disorder region, the entanglement is quite high, quite large. But when the disorder becomes strong, then it decreases to 0. So in the localized regime or strong disorder regime, the entanglement becomes 0. And the standard deviation has a peak around here. So this corresponds to the decreasing area. And so it means that the system becomes, here is the crossover point from the thermal to the localized regime. And right figure shows the twist overlap depending on the disorder strength. And the average and the standard deviation both are almost 0 in the weak disorder region. So it means it's in the thermal regime. But they both increases with the disorder strength. Just increases. Compared to this one, the twist over standard deviation shows almost no peaks. Maybe here looks like the peak, but it's not actually peak because the twist over the upper limit of the twist overlap is 1, so it's just an artifact of the decay of the disorder strength, the standard deviation. Now, here is the disorder dependence evaluated using the wave function after time evolution. And this figure shows the magnetization, average, and standard deviation. In the small disorder region, the magnetization is almost 0, which means delocalization. And in the large disorder region, the magnetization is almost equals to the system size. System size is the initial value. So it means it causes by the memory effect. So it means localization in the large disorder region. And the standard deviation has a peak around here, so it coincides with the crossover point between the localized and standard region. And here is the twist overlap, the disorder dependence. And actually, these are evaluated using the time dependence, the wave function, and compared to the ones evaluated using eigenstates, and they look very similar. So this means that the quantity twist overlap evaluated using the quantum dynamics have some show some properties of the eigenstates. So it's promising to explain some properties of the many-body localization. Now let's move on to the time evolution using quantum circuits. But it's there's numerical simulations and some real device computation. Now the time evolution operator is approximated using product formulas in the quantum circuit simulation. So, and the first order Suzuki-Torta decomposition is written by this equation. Here is UI and here is UTI. Then the quantum circuits look like this. Here M is the total number, repetition number. And the second order Suzuki-Torta decomposition is written like this. And this corresponds to this second order decomposition. But actually, this one and this one are the same. So it coincides with this quantum circuit. So these two are combined with one UTI block. So in the numerical simulation, actually this circuit was used. And in this work, we used quite small system, a tiny system, and it's only 5 qubits. And the final time is very short. And this slide shows the quantum circuit simulations results. And it is just the magnetization, the average of magnetization, and the standard deviation of the magnetization. And the label exact is the exact time of relation. And the bracket Pn corresponds to the pth order decomposition with the total number n. And as we see, the magnetization, the average magnetization increases with disorder strength. In the small disorder region, the magnetization is almost zero, nearly equals zero, which means the thermalization. And in the large disorder region, the magnetization becomes large. And it is slightly lower than the initial magnetization, but it is a sign of a memory effect. No? And in both panels, this one is just a standard deviation. In both panels, errors are negligible, which means the exact time evolution and the quantum circuit simulation are coincide almost coincide. But this one shows quantum circuit simulation, but the quantity is traced overlap. The absolute squared traced overlap. And these exact and bracket ones are meaning of the exact and bracket ones are the same, but ES is the first in this panel. ES means the evaluated using eigenstates around the center for the energy spectrum. So it is just for comparison. As you see, the twist overlap also increases with disorder strength. And standard deviation is a bit larger for the exact and the bracket ones, the simulations, than the eigenstate evaluated ones. The reason for the difference will be explained later in this talk. And we can see some errors are little errors, but in any way, the errors between the exact and the bracket ones, simulation ones, are small. But actually, in the real device computation, the errors becomes very apparent. This shows the magnetization in the real device computation. But it increases with disorder strength, but the errors are very big. The average and the standard deviation become smaller than the exact ones. The exact one is the same as the previous one. So in the large disorder region, this becomes almost like 3/4 of the exact one. So it is caused by the noise-induced errors. And as you see, please look at these small circle ones. Pure circle and the open circles corresponds to the total number n equals 10. And they look very similar behavior. But the triangle one, it's the total number n equals 15. So it's a bit smaller than the other two. So the errors are more significant for larger total numbers. And but the difference between the p equals 1 and 2, which means the green one and orange one, is almost negligible. And that's a kind of point. But twist overlap shows much worse results. It's almost like flat it increases with disorder, but very small changes. The average of trace overlap becomes much smaller than those of the exact, as you see. And the standard deviation becomes even smaller than the ES, the eigenstate. And errors are more as the magnetization, like the magnetization, errors are more significant for the larger total numbers. And as we can see in the triangle one. And but why the difference between such a difference between the magnetization and twist over occurs? And let's see the reason in the next section. And time reversion, exact time reversion shows some hints of the reason. This shows the time reversion of magnetization. Panel A, it corresponds to the weak disorder case. So, the magnetization decays, initially it's 5, but decays to 0 and fluctuates around 0 after or like t equals 1. But in the strong disorder case, the magnetization fluctuates around the initial value, which is a sign of the memory effect. Meanwhile, each graph plots 10 samples, so the color difference shows the sample difference, which is the time series of different disorder realization. So these are reasonable and as expected, but the twist overlap shows a bit different behavior. And actually, the panel C corresponds to the disorder case. The twist overlap decays faster than magnetization and decays to 0 and the fluctuates are here. So these decays are as expected, but the panel D shows the strong disorder case. It's very different from the magnetization. As we see, some samples like this one or this one oscillate with large amplitude, not like this, but very large amplitudes, which results in low time average. So, for example, these bright color ones have the average like 0.9 or 0.8, but these green or blue ones have maybe the average like 0.5 or 0.6. So these are the very big difference. And the noise-induced errors in amplitude can even lower the time average. So that's why the difference between the magnetization and twist over appears. And in addition, because we evaluate the twist overlap at the end of the time averaging here, so the average is very different between samples and samples. So that's why the variance or the standard deviation of the twist overlap is a bit larger than the one evaluated using the eigenstates. Now, let's move on to the conclusion. First, the crossover between the thermal and localized regimes can be detected by evaluating an observable after some time evolution. And in this talk, I used magnetization and twist overlap, and they can be easily obtained from the measurement of qubits in the quantum device. And the twist overlap evaluated using the wave function of the time version behaves similarly to that calculated using eigenstates under some condition. And another point is that choosing an appropriate observable is essential for detecting localization using a real device. And the magnetization is robust against noise, relatively robust against noise, noise-induced errors. However, the twist overlap severely suffers from those errors. Thank you for listening.
Thank you very much for the talk. So, time for questions. We have plenty of time. So, anyone? Please. Thank you very much for a very interesting presentation. There are different communities using different languages. So, some community talk about Mayweather localization, and some other community talk about singular phase transition, which is the same thing. You start from like a paramagnetic phase and go to a singular phase as we increase disorder. Can you explain what's the relation between these two concepts, the singular phase transition and Mayweather localization?
Actually, the many-body localization and the spin glass is a big difference. And in the spin glass case, it's only the disorder, but in the many-body localization case, we focus on some dynamical properties because the many-body localization is if there is a phase transition, if the MBA transition is a real transition, it is the dynamical system. So the dynamical transition, it is shown in the dynamics of the quantum system. Did they answer the question?
Yeah, to some extent. So it's, one of them is dynamical, the other one is like, but still, many of the localization we talked about eigenstates and eigenstate there, whether it's ergodic or localized eigenstates. As singular space transition, you focus on the grounded state, the same thing. So the grounded state will be delocalized and localized, but there should be some relation between the two. The same system.
Yes. Yeah, usually the quantum phase transition is the transition in the ground states, but the many-body localization is evaluated in the highly excited states. So that's why the dynamics and the phase transition needs in the many-body localization.
More question?
Can you make a comment about like I think that was the previous slide where like you were discussing how here like the twist like it's kind of like not robust against error. So I'm curious because it seems that it shows kind of some periodicity like with time. It's like something, it just looks like this, or is something hidden here? Yeah, like this one or like the bit smaller, like blue, the yellow. This just looks like this, or is something hidden here?
These lines, different color lines are different. Is different the sample. So this one is just for one sample. The trace overlap, and this one is another sample. So the system is different. The disorder combination is different between these.
Yeah, and my question is like, for instance, this is the localized state, right? On the right hand side.
Yes.
So in here it seems maybe it just looks like it, but for each sample, the has a certain period. Like for instance, for the biggest amplitude, it's like 2 point something, then the smallest one, smaller, and so on and so on. So I was wondering if there is any relationship. Just curious about no.
These have actually some periods, different periods and different amplitudes in the different samples.
Questions? Well, I have actually one brief one. Are you considering, because in the very beginning we were defining the Hamiltonian, Hamiltonian, are you considering, maybe you said already, are you considering create boundary conditions or open boundary conditions in the Hamiltonian?
In this case, open boundary condition.
And which are the boundary conditions that you're considering in the borders?
You mean if I make the periodic
If they are open, which are the boundary conditions that you are considering in the border?
Nothing in the end. Sorry. And so only one point in the edge. Only 5 systems, but between these ones, won't be 2. But the edge has 1 bond.
Okay, thank you. More questions?
Yeah, thank you for the talk. In the beginning, you showed the reverse linear feature and said that basically the simulation is like the constant part of the sketch in the middle, right? Could you comment on the timescales of the simulation versus the finite time ramp speeds, or like the time for this? And specifically asking you, could you implement this in an analog system like P-waves, for example? There, a specific feature.
Actually, I didn't compare the real time and the simulation time, but maybe we can estimate the time scale using the actual simulation of the decay rate. Maybe then we can compare the experiment and simulation. But I don't know the exact value of this one is actually in how somehow nanosecond or millisecond ID.
Okay, thank you. Any last question?
Hi, thank you for the nice talk. So I was interested to see when you add the noise into the quantum circuit setting, that causes the quality of the information to deteriorate, of course. But I was curious how you picked the Trotter numbers here, because I would sort of expect that, of course, if you decrease the Trotter number, you'll have shallower circuits with less noise effects, but then you'll start to see more and more Trotter error. And so I would expect sort of like a sweet point where you're balancing between the device noise and the Trotter error. Is that something that you explored?
Yeah, in the real device case.
Right.
Actually, I invested some errors source, but the readout errors are the most significant in these results, and the errors in the errors like the single qubit or the double qubit interaction that it can be estimated by the difference between these, because if the total number becomes large, then the 2-qubit interaction becomes much large. So we can estimate the error noise error from the comparison between these results. But I don't remember the exact numbers about the errors.
I see. And did you do this? What device were you using?
It was the IBM quantum device, but it was already retired. It's only 5 qubit chain distributed chain like system.
I see. And so did you look at using smaller Trotter numbers at all?
What smaller one?
Yeah.
No, I didn't try smaller one. Maybe we can try larger one in the future.
Thank you.
Okay, we are already in time, so let's thank again the speaker and all the speakers.